Asymptotes for AP Calculus on the topic of improper integrals with vertical asymptotes, continued. So this one says evaluate each definite integral if it converges or show that it diverges. So what's different about these, they don't have lower upper limits that are negative infinity or infinity, like the other type of improper integrals. But what happens is, notice, if you look at what makes the denominator 0, that's when x equals 0. We've got a vertical asymptote there. And the key is it's in the interval. In this case, it's our lower limit. Most of the time with, I guess you could say, proper definite integrals, it would be when the function is continuous on the interval, from the lower limit to the upper limit. But here it's not continuous right at 0. So if it's an endpoint, you can integrate like normal. You just have to keep in mind some weird things might happen, and it might end up diverging when you go about trying to evaluate. It's not guaranteed to converge to a specific number. So we just have to keep that in mind as we go through the process. So this one we've got the integral from 0 to e, and then natural log of x divided by the cube root of x. So in this form, you can see we'll use substitution. If you say you go to natural log of x, the derivative is 1 over x. That's not going to help you cancel out a cube root of x, so that wouldn't really work here. And in this form, there's no quotient rule for integration. So the closest thing we have to the product rule is integration by parts, but that requires the things to be multiplied together. So we can rewrite this as x to the negative 1/3. We bring it up to the numerator, and then times natural log of x. So now they're multiplied together. Now we can attempt to use integration by parts. So again, to figure out which one is set equal to f of x and which one is g of x, I'll just write the formula over here, just to refresh your memory. So when you have one is f of x and one is g prime of x, what it ends up equaling is f of x times g of x minus integral of f prime of x times g of x. Remember, it has the same components as the product rule, they're just in a different order in different places. So the way to figure this out is based on which one's easier to find the derivative of. In this case, they're both, you can find the derivative of both of them, or which one's more easily integratable. This one's easy to integrate. Natural log of x is not easy to integrate. It requires integration by parts itself. So that's how you know in this case to set f of x equal to natural log of x. That simplifies a little better with the derivative too. And then x to the negative 1/3, even though they're both pretty easy derivatives, and then set g prime of x equal to x to the negative 1/3. So then when we find the derivative of f prime of x, derivative of natural log of x is 1 over x, and then integrate g prime of x. Using our power rule, we add 1 to the exponent, adding 3/3 gives you x to the 2/3. Dividing by the 2/3 is the same as multiplying by 3/2. Notice this is not one you could use the tabular method on, because this is x to the negative 1. If you keep taking the derivative of this one, it will never be 0. The tabular method only works when the derivative here eventually becomes 0. So we just have to do it the regular way for integration by parts using this formula. So f of x is natural log of x times g of x, 3/2 x to the 2/3. And this one's a definite integral, so this is the part that's already integrated. So this one would be evaluated from 0 to e. And then minus the integral from 0 to e. This is the part we still have to integrate. F prime of x is 1 over x. times g of x, 3x to the 2/3 over 2 times dx. Okay, so now let's, on this one you can simplify a little bit. You could pull out the constant of 3/2 here. And then if you switch this to radical form, it might be a little easier to work with. This is the same as the cube root of x squared times natural log of x. And then let's go ahead and simplify this one. We can pull out the 3/2 here times the negative that's already on the outside. So this would be negative 3/2 out here. And then you can simplify what's inside. You got x to the 2/3 divided by x, which is like x to the first. And that's the same as 3/3, so you would subtract the exponents. X to the 2/3, so 2/3 minus 3/3 gives you negative 1/3. And so now, when you're using integration by parts correctly, this should be a simpler integral than our original one, which you can see it is. If it's getting more complicated here, then most likely you reversed f and g prime here. All right, so let's keep working out this one, and then we'll substitute it all in at once here. So, got negative 3/2. When you integrate x to the 1/3, negative 1/3, notice we kind of already did that right here. It happens to be the same thing here, so we get x to the 2/3 times 3/2. From 0 to e. Then you can pull out the constant 3/2 times the negative 3/2 that's already out front. That'll give you negative 9/4. And then if we switch this to radical form, cube root of x squared. All right, so let's take what we've got here. I'll circle it here for now. We've got this. And go ahead and substitute in. So far, it's been like a pretty normal integration by parts problem. But here's where it gets a little weird. So we've got 3/2 on the outside. And then we substitute in the upper limit of e. So that'd be cube root of e squared times the natural log of e. And then minus lower limit is 0, so cube root of 0 squared times the natural log of 0. And that's where you might notice it gets a little weird. We'll come back and talk about that natural log of 0, because as we know, that's undefined. And then we've got the negative 9/4. Cube root of e squared minus the lower limit, cube root of 0 squared. All right, so with this natural log of 0, we know that's undefined. So if this was by itself here, if it wasn't multiplied by this cube root of 0 squared, that would be undefined, and we would know at this point that this integral diverges. However, being multiplied by 0 actually makes a difference here. So we know this is 0, cube root of 0, 0, 0 squared is 0. And if you think about the graph of natural log, now we can't plug in 0, but what we can see is what it's approaching from one side. So here's our sketch of natural log of x. We know 1 at 0. And it looks like this. So notice as it approaches x equals 0 right here, it only approaches it from one side, from the right. Notice it's heading to negative infinity. So this is going to get really close to negative infinity, which again would normally mean that it does not exist. But because it's multiplied by 0, even if it was negative infinity, 0 wipes wipes that out. Because it's multiplied by 0, this whole thing is 0 rather than infinite. So it's not going to end up being one that diverges. But again, that's only because it's being multiplied by the 0. So let's see what else we've got left here. Natural log of e, that's e to 1 exponent to e, that's just 1. So here we just have 3/2 cube root of e squared, and then minus 9/4 over here, cube root of e squared. As again, this one's 0 here. So you can leave it like this, that would be correct. But if it was multiple choice, they'd probably get a common number, multiply this one by 2 over 2. So you'd end up getting 6/4 cube root of e squared minus 9/4 cube root of e squared. You can see those are like terms now, what we commented on there. So 6/4 minus 9/4 would give you negative 3/4. Cube root of e squared. So that would be a more simplified answer. And since we got a specific number here, this one, that's what we got when we evaluated it. So it does converge to a specific number. All right, let's take a look at another one here. On this next one, it says evaluate each definite interval if it converges or show that it diverges again. So this one, notice that we factor the denominator into x minus 4 times x minus 2. If we set that equal to 0, notice we've got vertical asymptotes at 4 and 2, and 2 is what makes this improper. That is in the interval between 0 and 3. So this case, instead of being an endpoint of the interval, like the other one was the lower limit, this time it's right in the middle of it. So if that's the case, if you have vertical asymptote, it's not the lower limit or the upper limit, but somewhere in between, that means we're actually going to have to split the interval at that vertical asymptote. So eventually, once we figure out which method to use to integrate this, we're going to have to split it from 0 to 2, the asymptote, and then from 2 to 3. If you don't, you can oftentimes get the wrong answer if you don't split it at that vertical asymptote. All right, so we've got the interval from 0 to 3, and then you can see which method we have to use here. Sorry about that. Is with these two factors here, u substitution wouldn't work here. The derivative would have x's that don't cancel out, but we've got two different factors, so we can use integration by parts. By partial fractions, I should say. Or sometimes it's referred to as decomposition of fractions. So we have to set our original one, 6 over x minus 4, x minus 2. We want to decompose that into two fractions. The single fraction, one of them is a over x minus 4 plus, second one is b over x minus 2. Now we need to figure out what a and b are equal to, what those constants are. So first thing we can do is this, multiply the whole equation by the least common denominator by x minus 4 and x minus 2 to reduce out all the fractions. So when you distribute that times this one on the left side, it wipes out both of those in the number, we're just left with 6. Equals, here the x minus 4 is reduced out, so you're just left with a times x minus 2. Plus here the x minus 2 is reduced out, so you're just left with b times x minus 4. And then you have to strategically choose x values to help you solve for a and b. So if we first start by letting x equal 2, notice that we'll make this one 0, wipe out the a's, so we'll get 6 equals a times 2 minus 2 plus b times 2 minus 4. We'll get 6 equals, that wipes out the a's, you get negative 2 times b. Divide by negative 2, so b is equal to negative 3. So that's what's going to go on the numerator of the b, right there. And then, same thing to solve for a, strategically choose what will make the b's get eliminated. So let x equal 4. That'll wipe out the b term there, so we'll get 6 equals a times 4 minus 2 plus b times 4 minus 4. Again, that wipes out the b's there, 0b, and then we get 6 equals 2a. And divide by 2 gives us a equals 3. So here they are opposite values, but that's not always going to be the case. They're not always opposite with partial fractions here. Just happens to be on this particular problem. And then we can rewrite our integral. Now normally I would just rewrite it as two separate ones from 0 to 3. We can do that at first here, so we can write, let's do that first here. So one step at a time, 0 to 3. A was so it was 0 to 3. A was 3, so this would be 3 over x minus 4 plus 0 to 3. B was negative 3 over x minus 2. However, because there's a vertical asymptote at 2, if there wasn't a vertical asymptote, we could just evaluate each of these. We've got to split each of these and go from 0 to 2 and then 2 to 3. So if we write that out here, first one will be 0 to 2, 3 over x minus 4, plus 2 to 3, and then 3 over x minus 4. And then, normally it'd be plus these, but I'm going to pull out this negative here to make it a little easier here. So this will be minus integral 0 to 2, 3 over x minus 2, and then because the negative's out in front of both of them, instead of split it with a plus, that negative gets distributed to both of them. So it'd be minus integral from 2 to 3, 3 over x minus 2. So we end up having 4 integrals because of that. So now we can integrate those. Notice each of these fits the natural log. You can pull out the constant and you can use the u substitution shortcut on all these. So we get 3 natural log opposite side of x minus 4. Evaluated from 0 to 2. You can leave the 3 on the outside. Plus 3, same thing, natural log opposite side of x minus 4 from 2 to 3. Minus 3, natural log, again the u substitution, u is just x minus 2, the derivative is just 1, so we can integrate it just like this is a single variable using the shortcut for u substitution. And 2. And then finally minus 3. Natural log absolute value of x minus 2 from 2 to 3. So now we just have a bunch of substituting to do. So here we've got 3. And when you plug it 2, here's where the absolute values start having some effect here. 2 minus 4 is negative 2, but the absolute value turns into positive, so it would be natural log of 2 minus, when you substitute in 0, that would be negative 4. Absolute value makes it positive 4 minus natural log of 4. So far, that's pretty normal there. Plus 3, substituting 3 there. You get negative 1, 3 minus 4, but absolute value makes it positive 1, so natural log of 1. Minus, you plug in 2, negative 2, natural, absolute value makes it positive, so natural log of 2. Again, so far, pretty normal. Then minus 3, you substitute in 2, we get 0, natural log of 0. That's where it starts looking weird here. Minus, when you substitute in 0, it's a negative 2, the absolute value makes it positive 2. And then minus 3. Natural log of 1, and you substitute in the 3. Minus natural log of 0, 2 minus 2. So, the undefined ones here, we have a couple of them. Undefined, and this is undefined as well. And notice this time they're not multiplied by 0, so they're not going to get wiped out by a 0. So because of that, even if you only had one of these, that's what tells you this one diverges. Versus, I'm pretty sure on this one, if we hadn't split it up, if we had just gone 0 to 3, 0 to 3 to 2, we would have gotten an actual answer that would have ended up being wrong, because it actually diverges. That's why it's important to split it up there at the bird box. All right, one more let's take a look at. This one's a little trickier. So if we set the denominator equal to 0 here, this one wouldn't give you any zeros, because if you subtract the 1 and square it, well, you can see this, this is never going to be 0 here, because the squared principal root of x's will never be negative plus 1s. But this one could be 0 at x equals 0. And notice that's an endpoint. So we don't need to split this one up like the last one, but we do need to keep in mind it might diverge. We might get something weird here, because there's a vertical asymptote right at the lower limit. So it's kind of in a weird form. You could distribute this out, but there must be a reason why they put it in this form here. It doesn't quite fit partial fractions, because these are not standard polynomial ones here. So that makes you think, well, why would they write it this way instead of just making it x plus the square root of x? You distribute it. Well, it must be so it's easier to use substitution. So u would equal, well, this one is a little more complicated than this here, so let's try setting equal to the more complicated one to make our integral simpler. And that's, if we rewrite that, the same as x to the 1/2 plus 1. So then when we find the derivative, using the power, we get 1/2 x to the negative 1/2. Which if you simplify it, 1 over 2 square root of x. And then when you derive a fraction like that, it's probably just be cross multiplied to solve for dx. So dx times 1, dx equals 2 square root of x cubed. Substitute that right in there for dx. Then, we also need to convert the lower and upper limits, remember, since we're using substitution right here. So I'd be substituting 9, square root of 9 is 3 plus 1 gives you 4. and substitute in 0, 0 plus 1 is 1. And let's see what we have left now. So now we still got 1 over square root of x, and now we replace this one with u, and then dx is 2 square root of x du. So now you can see the square root of x is reduced out, which is what we wanted, to get all in terms of u. We can pull out the constant, the coefficient of 2, out in front. And then what we're left with is just 1 over u, or you could write u to the negative 1 du. So notice we accomplished what u substitution is designed to do, take a more complicated integral and turn it into a simple one. So when you integrate 1 over u, just like the ones we did on the previous one, just this one doesn't require u substitution now at all. We already did that. Natural log absolute value of u. And remember, since it's a definite integral, we don't plug this u square root of x plus 1 back in here because we've already converted the lower and upper limits. So we do 1 and 4. So we'll have 2, substitute in the upper limit of 4, so you get natural log of 4 minus natural log of 1 here. The absolute value didn't affect either one. But the natural log of 1 is 0. It's an e to 1 exponents 1. So we just end up with 2 times the natural log of 4. So the answer could be written that way. That's pretty simple. Or you could also use the log properties, bring the 2 up to be the exponent of the 4. And you could also write it as natural log of 4 squared, which is natural log of 16 would also be correct either way. And that concludes the notes for AP Calculus on the topic of improper integrals with vertical asymptotes continued.